So we'll be doing some software algorithm tests. I hope you're all ready for it. Hopefully I have a few little things that are at least a tease into some exciting stuff I've been doing. And part of that's Avalanche. We have some updates coming over the next few weeks. Probably by the time this is actually up on YouTube, these things will all be released. But I wanted to talk a little bit about the background behind some of them, how they work, as it specifically relates to C4, because that's where all of this stuff comes from. So we have a new website. If you were to go there right now, it looks like that. But it's about to look like this, with new GUI for file navigation, which I'll show you in a second. But I wanted to talk a little bit about everybody today has been talking about the same kinds of problems, but from a very specific point of view, kind of embedded in the conversation, that pretty much everybody in the entire world of distributed systems, this is pretty much how they mentally model data on big networks and how they describe the process. The problem with the way that we consider all of our data today in distributed systems is that we think in terms of transactions. We think in terms of moments in time where an event occurred or where systems are driving events. Render queue manager might be an example of this, where it's listens for work to be done, and once it gets some work, it starts the work, and if a machine fails, it notices and requeues it and so forth. Pretty much everything we ever think about or do with respect to these kinds of distributed systems is event-driven like that, including the way we as human beings work with it. For example, when you want a file that you're going to download from the internet, you have to download it. There's a point in time where you're executing that action, and if it fails, then you got to do it again. And underneath the systems, the software is thinking and acting more or less the same way. And this leads to an extremely complicated computational model, which some people will know as being able to just get consistency and agreement between multiple actors within these kinds of automated systems. Another term for it is CAP theorem. We won't get into it, don't worry. But it does mean that you can kind of only rely on certain aspects of systems, and it makes them very, very, very complicated to engineer. The example of this, which this may or may not actually illustrate very well, is like if you're working with somebody who is on the ground in their office doing work right on the files themselves, and you're doing similar work on similar files on an airplane, disconnected from the internet. Then you start to disagree in terms of the work that you're doing. And then once you come back together again and try to find agreement, there is confusion, right? Humans can solve this problem, computers not quite as well. But there are algorithms for doing this. You elect one machine to be the leader and so forth. Perfect, thanks. And good timing too. Because one of the great software projects that I think originally came from a team that was originally at Google. I just saw this really cool demo of it online. I thought, yeah, oh, that's it. So this is a Raft algorithm. It's a strong consensus algorithm. It just shows how on the simplest level, one service, trying to keep one service absolutely reliable. And this is an extremely complicated algorithm that has, in this case, these 5 servers that are trying to maintain synchronization. I think you can kill one of them. Whoops. Or I can just not know how to use it. But the point is that you can play with this example and try to disrupt its ability. And the algorithm works really well. But it has to have half plus 1 of all of the machines running. So 3 in a set of 5 have to always be online at the same time, or the system will fail. So that by itself sounds like a pretty high standard of reliability. But for certain types of applications, it really makes a lot of sense. Things like, real-time bank transactions and so forth. So let's see here. Where are we? Okay, so before we get into that, that's a lot of what C4 was built on, was built to solve. So for those of you who don't already know it, I just thought I would show some physical examples of this real quick. This is on the GitHub site. So there's some comparisons here between C4 and other numbers. A lot of people comment on it being a long number, but of course most of the time these are numbers that are handled by computers. But it actually does have some very carefully considered human usability issues. For one thing, it's much shorter than SHA-512, as is typically encoded. And you can theoretically make a SHA-512 hash of content shorter in ASCII with a base64 encoding, but you can't tell what that number is, whereas C4 always starts with C4 and always looks the same. So the other big advantage is that when you interact with these numbers, you can't select any of them just by double-clicking on them. You can select more than it, or you can select some fraction of it. C4 IDs, you always select the entire one. It makes copying, pasting, and just interacting with these as identifiers much, much easier and less error-prone. That's just kind of an aside, but it just shows the kind of work that has gone into figuring out this system and making it both ergonomic and useful from a computing point of view. So the reason that all of this came about is specifically because of this consistency problem. So when you talk in terms of, that's not playing, that's just editing. Here we go. All right, so here's the interface for Avalanche. Now, so the idea here is that what one really wants to be able to do is, this is pretty much the most complicated view you can put together in Avalanche. But at its core, it's basically just a file navigator. You don't have to have this metadata view that's up on the right-hand side. But I just put it up to show what kind of things you can have in there. The idea is that it's pretty much just like Finder or Explorer. But because of the C4 IDs, you can easily track all files that exist in your access anywhere in the world. Millions, trillions, billions of files, because what C4 IDs give you is an ability to find agreement between different systems without having to be in constant, immediate contact with all of them. Once you have relatively small updates from these different systems, you can generate a completely accurate, completely reliable image of what those files and what those locations are, and whether you have a copy or whether those are unique in that location or what other information you have. And the other thing that C4 IDs give you is this ability to bind things together. Because once you have, say, a bit of metadata, here, for example, we have some XML camera metadata from a F-55 shoot. It has time codes in it and resolutions and so forth. If you were to separate this XML file from these internal files, you might have a few little names of files that you could kind of do a search on, but it's a little bit dodgy, a little bit unreliable. Basically, you want to keep these things together. With C4, if you put the C4 ID of the files you're talking about in the metadata, then those two things are inseparable forever, basically, if they still exist, because you can't fake a C4 ID. If you have a C4 ID in some metadata, and you also separately have something that evaluates to that C4 ID, then those two things belong together. Nobody could have faked that relationship. The idea is that you can then either have data that you can find the C4 ID of and then search, even a text search of files on disk. It doesn't have to have any infrastructure at all, and you can find the metadata that's associated with it, or the other way around. You can have the metadata, you can ID your assets, and find which one is the one that relates. So for the first time pretty much ever, we have an identification system that is completely reliable even if infrastructure shuts down, right? If you actually just look at, assuming it's not encrypted, if you actually just look at this stuff on disk, you can reconstitute the relationships and the connections. Things like editorial EDL files and so forth can have a completely reliable relationship with things, even if you just send the EDL in an email and none of the media. It just arrives separately, and nobody makes any particular effort to try and sync them up. They just will. So Avalanche's interface gives you basically that very simple ability to interact with all your files, no matter where they are, and use and attach metadata to them. In this case, you can have chat histories, you can take notes, and all these things can easily be bound to the things you're talking about and move wherever they need to move. If it's another person that's in a conversation with you, then they would have the copy of the conversation as well. And of course, all the communication between entities is encrypted. So I already did that. So the other aspect of Avalanche and C4 that's really beneficial to the cloud is what I've heard some of the people talking about today, is all the complexity related to finding out what files you have, where they are, if they're in sync, and so forth. And one of the most common tools for doing this is rsync, sometimes just regular file system interfaces like NFS. So C4 can actually outperform rsync, because rsync is fantastic and it's got some really incredible engineering in it. But what it does is it considers amongst the files you've asked it to transfer, what is the minimum set of things that it can transfer across the wire, give or take compression and some other features. So if you do, in this example, if you have straight copy, you know how that works. You've got to copy every file. And you don't know necessarily if one's in sync or out of sync. You can look at the metadata and the system information, see if a date's changed, but that's not particularly reliable. rsync can take even portions of files and only transfer the minimum, and it checksums the rest of them to make sure that it doesn't need to transfer if it doesn't. But Avalanche, or C4 more generally, C4 can actually consider all the possible files. Not just the files you've asked it to transfer, but all possible files. So if the remote system has a file that is the file that you need to transfer in some other context, in a completely different folder or whatever, then C4 can say, well, I'll just copy the one I already have locally, and I'll just make another copy at this file path. So another thing that goes into the open source stuff that we're talking about, just briefly touch on this, is an archive format. We're not, it's early yet, we're not super pushing on it being a standard, but that's probably ultimately the way it will head. It provides a lot of features. We need some updates. tar is what's still pretty much commonly used inside of most of these applications for network protocols and so forth. And it's just incredibly old and has all kinds of just usability issues with it. Because the C4 archive allows you to store files in the archive, or because you can always absolutely be sure that you've got the same file, you don't necessarily have to include the actual data with the archive. It can reconstruct that at another time. It also has the ability, it has a header that has what's called a Bloom filter, which is a very efficient way to test whether or not a file is in an archive. And this is particularly interesting because you could have petabytes and petabytes of storage and not know much about it, not know that you needed to have some file that now you need to have. And instead of having to open up all of them and consider all of them, or even open up the entire header and consider all of them, you can just test the ID against the Bloom filter, which is only a very small portion of the header, much less than it would take to actually list all of the IDs in the file. And it will tell you with a certain percentage whether it's in the file, or 100% if it's not in the file, it'll say it has no false negatives. So if it says no, then it's absolutely not in the file. And other little features. OK, so I'm going to talk about what this means in terms of how you work with files in the cloud and for media production, and how Avalanche's file management is engineered. And the key idea here is this idea of imperative versus declarative, because the system I was just showing you with the strong consensus algorithm Raft, trying to get 5 servers to stay in agreement under various levels of failures, all of that is shielding the system against a moment in time where it's not reliable for some window of time. But the idea behind, so I would characterize that as an imperative style of thinking and style of programming, meaning every single moment, every single step counts. It's important to make sure they're done correctly, in the correct order, in the very rigid way. Declarative, on the other hand, means I want to just state the way that I would like it to be, right? And the particulars of making it that way are not relevant to my statement, right? So that's the difference between the way all of the C4 framework and universe kind of have been constructed, is this idea of building a declarative way of thinking about media production. Because unlike bank transactions and airline ticket sales and things that require very hard synchronization problems between 2 customers getting the last seat on an airplane, or bank transactions where money has to be at the right place at the right time and so forth, media production typically does not have those kinds of constraints, the kinds of constraints that require strong consistency and active services like that. Usually, we're creating these single copies of things. These, you do multiple versions, but those multiple versions of things tend to be their own immutable version of whatever it was. So that's kind of the idea behind C4, is that every single possible file, you can throw them away, but every single possible file could plausibly continue to exist. Every single version of a file that you've written over that same file name could continue to exist. It just depends on how you archive it and maintain it. So just applying this idea to the very simple idea of file navigation, knowing where your files are, moving files around, and determining where they should be, I wanted to show what the difference between imperative thinking about it and declarative thinking. Imperative would be to issue the instructions to do the copying, right? So, for example, a copy or an rsync command, and that seems very small and convenient, and you can even do what I've done here with the cp command, where you say, just give me everything, just copy everything that's in this folder. But what happens when these commands fail? You've got to run them again. Well, can you figure out where to run them again from? rsync can do a pretty good job of figuring out where it left off, but copy, cp-r, it won't. It'll just copy everything right from the beginning again, as if you did no work at all. And even though rsync does do a very efficient job, it will still have to kind of catch up to where it was, recheck all of its previous work and progress and so forth. But a declarative way of working, turns out, it looks a little bit more verbose, because what you're doing is you're actually declaring, these are the things I want in location 1, these are the things I want in location 2. You just state them literally. Here's the list of things that I want and where they should be, right? There's probably ways that you could express that in a slightly more, visually easy way, but what's deceptively powerful about this is if there's one missing, you'll see it, right? You can actually see the differences, you can compare the differences, and more importantly, the machines can compare the differences. So what happens with Avalanche is that you say, for example, drag and drop from your data center a couple of petabytes of storage of files over into some other location. What happens in the system is that all of those files will represent transferred immediately. Anybody who has access to a view of those various systems will see the files instantly. They won't literally be there yet, of course, but you can see that that is the intent. Some user who had the access to do it has expressed the intent that these files are here. The system then, without human interference, can work indefinitely in the background until that state of affairs is true, which means it doesn't have to be aware of every moment of every second that a copy was being made or failed or whatever, which is exactly what you need in media production, because sometimes what you want is to be able to say, I want all of this media that I have on location on set in Abu Dhabi, and I need to have it in the 20th Century Fox backlot also. That may arrive by high-speed Asperalinks. It might arrive, generally more commonly, it arrives as hard drives. Those things come, and it doesn't matter which system does the copy, because at any given moment in time, the C4 and the declarative point of view can just look, is this the way it's supposed to look? It isn't? Okay, keep copying. It is? Done. Whether the system itself did the work or not isn't part of the requirement, which is where there's this disconnect between the way that engineering is done for internet, web types of applications and media production company applications. It's a completely different way of working that we can take advantage of in media production. You just can't nearly so well with active live services. And there's a dark view of the interface as well. And that's it.